Hi, good morning, everyone.
Good morning, Kostas.
Good morning.
Good morning, Panagiotis and Lee.
No to o 14 średnio, okej.
Good morning, everyone. We'll wait a couple of minutes more for others to join, and then we will get started. Okay, let's start. Good morning, everyone, again. And thank you for joining today's webinar. My name is Sophia Adam, and I work for Insights Consulting, who leads the communication and dissemination activities for the TERRA project. I will be moderating today's session. Before we begin, just a quick note for you. This webinar will be recorded. So if anyone does not wish to be recorded, please let me know now in the chat, or feel free to turn off your camera. Is there anyone who does not wish to be recorded? Okay, if there are no objections at this point, let's continue. Today's session will focus on the TERRA demonstrators and how Earth observation and Copernicus services are applied across different environmental use cases. We will start with a short introduction to the project, followed by presentations from our demonstrators. And finally, we will close with a discussion and Q&A session. You are welcome to submit your questions in the chat throughout the session, and we will address them at the end of each presentation or during the discussion, if needed, of course. Well, to start, I would like to give the floor to the TERRA Coordinator, Kostas Kolomvatsos from the University of Thessaly, who will introduce the project and its vision to you. Kostas, the floor is yours. I don't know if you want to share your screen.
Hi, Sophia. Good morning, everyone. Thank you for the introduction. Yeah, I'm going to share my screen.
Okay.
Give me a minute.
Of course.
Can you see my screen?
Yes, we can, Kostas. Very well.
Okay, perfect. So this is the third slide. Yeah, thanks a lot for the introduction. I'm Kostas Kolomvatsos. I'm representing the University of Thessaly. University of Thessaly is the coordinator of this project. We're happy today because we have the opportunity to realize the first webinar of the project with the target to present the demonstrations, our demonstrators, where we're going to figure out how satellite data and not only satellite data, institute data can be adopted, can be processed in order to provide, to deliver knowledge, to provide useful services to various application domains. Starting my presentation, in this slide you can see some details, some information about the project. The contribution of the European Commission is around 2 million. We are 9 countries on board. The project started on January 1st, 2025, and it's a 3-year project. You can see in the list of partners that we have partners from Poland, from Greece, from Germany, from Cyprus, United Kingdom, Luxembourg, and Italy and France. And these are the objectives of the project. The first one is related to the development of our services. Based on our services, we are targeting to implement 3 product chains for the 3 demonstrators. And for all of them, our intention is to build the services in a way that will be reusable from any interested actor in order to be adopted in different domains. And as I said, to deliver knowledge, to deliver useful information and results that can support decision making. For all these services, Copernicus data, Copernicus applications are at the core part of our research. And we are planning to integrate all these services in order to formulate this novel product chains. The second objective is related to the artificial intelligence. As you understand, it is very important for our project because One of the results is to develop this pool of AI algorithms that will assist to build digital twins for the demonstrators. And based on these algorithms, we are able to process images or any other data that are provided by the Copernicus services and EC2 devices, as I said before. The third objective is to evaluate the quality of the implemented services and demonstrate the impact of our product chains that is related to the integrity policy of the European Union. And of course, this should be presented through our use cases, which will be realized in Greece, in United Kingdom, and in Poland. Later on in this webinar, you can see more details about the demonstrators and how we're going to integrate all this data, all these intelligent goodies, let's say, into one platform for supporting decision making. The fourth objective is related to the business models that we can build upon the provided services. We would like to highlight the scientific, the social, and the business perspectives of our work in order to expose how the implementation of additional services and extensions to our services can be easily realized in order to mobilize people and exhibit market adoption of our results. The final objective is a typical one, and it is related to the outreach activities, the dissemination communication activities. This webinar is in our plan for dissemination, for disseminating the project into a wide audience. At the left, in this slide, at the left, you can see the target end users, governmental agencies, policy makers, public authorities. Citizens and wider public are also in our targets, and from the technical perspective, focusing on the technical perspective of the project, we can have as end users ICT providers, system integrators, equipment vendors, and application developers. At the right of this slide, you can see the main expected results that are related to the objectives that presented in the previous slide. Our platform, where all Copernicus data, all data are aggregated, integrated. We rely on data fusion techniques in order to merge this data and provide useful knowledge. The AI results, for sure, will be presented through the platform. We have the digital twins. This is a very interesting and innovative aspect of our work. In these digital twins, we embed the results of the AI algorithms. We embed the results of the data management. We are also performing data augmentation in order to produce more data. You may know that, for instance, satellites cannot provide data daily, on a daily basis. So it will be useful to augment the data and produce more bigger data sets that can support the process that we're targeting to. Heterogeneous data processing, knowledge extraction, and another aspect is the adaptive and self-learning capabilities of the digital twins. The AI models, I think that it is easy to understand that we are building some pipelines of the processing activities based on the AI models. And we are building a repository where all these AI models are stored and be ready to be adopted. The final result will be the data sets and data maps. We will provide some visualization interfaces. Through these interfaces can invoke, can use the provided service, and you see the results of the application, the product chains. And we have some capabilities of data pre-processing in preparation before these data are fed to the AI algorithms. So I don't want to waste your time because I think that the next presentation are more useful for you because we will present the details for our demonstrators. So that's all from my side. I would like to thank you for your attention.
Thank you, Kostas. Thank you very much for your presentation. Before moving on, are there any questions from the audience to Kostas about the general, let's say, overview of TERRA? If not, we will continue with the next presentation. We will move to demonstrator 1, focusing on water contamination monitoring. I would like to invite Panagiotis Oikonomou from the University of Thessaly. Panagiotis, good morning.
Hello, Sophia. Hello, everybody.
Hello.
Can you hear me?
Of course, we can hear you. The floor is yours. I don't know if you will have a presentation for us to share.
Yes, let me share my screen, please. Can you see my screen now?
Of course, yes.
Okay, hello, everybody. My name is Panagiotis Oikonomou. I'm a member of the University of Thessaly team. It's a pleasure to present our work in the TERRA project, which focus on the water pollution demonstrator. Before we delve in more details, let me briefly introduce where our work fits in the TERRA ecosystem. The overall TERRA ecosystem and the TERRA platform is built around 3 main demonstrators. Each demonstrator is addressing a different environmental and climate-related challenge through the combination of 3 things, the artificial intelligence, Earth observation, and digital twins. Our work is the demonstrator 1, which deals with the assessment of water contamination in coastal areas and across the water cycle in general. Water pollution is a very complex problem that evolves through rivers, coastal zones, and surrounding ecosystems. And for this reason, we combine AI models, hydrological analysis, remote sensing data from both satellites and USB unnamed surface vehicles. And finally, we combine digital twin technologies to create a continuously updated digital representation of the water system. So, why this demonstrator matters? Because water pollution has been increasingly important in recent years, especially because the pollution is strongly affecting ecosystems, public health, and climate-related services. And also, water quality is monitored in different ways across Europe. We may use drones, satellite images, in situ sensors, ships, or combinations of these sources. But the real challenge here is not only to collect data, but bring all these data sources together in one system and use them to predict how the pollution will evolve over time. And this is actually where our work adds value. As in TERRA, we move beyond simply monitoring, and we have a goal to combine monitoring, forecasting, hydrological movement, biochemical understanding of pollution into a single end-to-end system. Another important aspect is that we monitor pollution from the river all the way to the coastal area, so we can understand how contamination travels through the entire water cycle. And in addition, we also use USVs. The USVs collect real measurements from the rivers and the coastal areas, and these give us a more richer and realistic picture of water pollution for better decisions, for better future decisions. This demonstrator has 5 main objectives. The first objective, here, we aim to develop a water pollution model based on Copernicus data and Copernicus services, so we can exploit observations and Copernicus products. Then the second objective is to build a USB-based pollution model with real measurements collected by the USB along both the river and the coastal zones. Third, an important objective is that we try to fuse we will fuse the models, combining both satellite intelligence and in situ measurements through model integration. The next objective is to apply all this integrated approach in a river delta scenario where pollution needs to be detected not only in the water but also in the surrounding areas. And the last objective is to detect the distribution of pollution, but with a focus on the direct or indirect effects in the human health. So in this slide, you can see the use case scenario of our demonstrator, which is located in the Spercheios river basin in central Greece. This is the Phthiorida region and the coastal area of the Malian Gulf. We selected this area because it provides a good real-world environment to study how pollution moves from inland water rivers toward coastal and marine ecosystems. And as you can see, the Spercheios River flows into the Malian Gulf. And from there, the impact may extend much further, potentially across the central Greece area, entire central Greece area, nearby coastal zones, the Evia Island, right here, or even the wider parts of the Aegean Sea. This makes this area understandably highly important, not only environmentally, but also socially and economically, as this region includes around 550,000 people in central Greece, with around 108,000 people in Phthiorida alone. And at the same time, the local economy mainly depends on agriculture, forest, and fisheries. All of these are highly sensitive to water quality. Our main objective in this scenario is to detect the pollution routes in order to understand how the contaminants are transferred by the river towards the coastal zone and how they may even further propagate. And this is important because if we understand, comprehend these routes, we can better support early warning, risk assessment, and the selection of the most appropriate mitigation actions for the stakeholders in general, especially local authorities. Based on this scenario, the next step is to showcase how we digitally represent and monitor this system in TERRA. And actually, this is where our hydrological and water pollution digital twin comes in. The digital twin combines three main streams of intelligence. The first stream is the Earth observation stream, where we use Copernicus satellite data to monitor large-scale environmental changes and extract water quality indicators like the water quality index. The second stream is the USV sensing, where the USV is equipped with multiple IoT sensors to provide local real measurements inside the river and the coastal zone. These measurements are very important for us because we will use them for both validation and local prediction. The third stream is the hydrological stream, the hydrological modeling component, which help us understand the water movement, the direction of the flow, and the accumulation of the flow. And this will help us estimate how pollution is transported through the river or the coastal areas. And inside the digital twin, these three streams are continuously fused into a unified digital representation of the water system. The digital twin delivers several outputs. For example, the pollution pathways, the affected areas, and information related to decision support, and help us to understand where pollution is moving and what mitigation actions may be needed. In the next slide, we dip into the core of the digital twin. On the left side, you can see that we integrate multiple input sources, including Earth observation data, USB data, measurements, terrain information like the digital elevation models, and external APIs. All these inputs continuously update different digital twin states. We have three main states inside the digital twin. The first is the hydrological state, which captures how water moves through the system using flow direction, flow accumulation, and several slope and new river network or other terrain-based information. The second is the observation state, where we combine biochemical indicators from satellite Sentinel-2, such as the concentration of chlorophyll, the density of cyanobacteria, the turbidity, the CDOM, the color dissolved organic matter, or dissolved organic carbon, or the water color. We also collect data not only from Sentinel-2, but from Sentinel-3, like sea temperature, water reflectance, and depth, along with data and measurements from the USV, like turbidity and pH. And the third state is the prediction state, where advanced LSTM models, long short-term memory AI models, forecast future water quality conditions. All these states are fused in the unified digital twin state, which then generates pollution forecasts, pollution pathways, hazard maps, and also generate a fused water quality index. And actually, this is the main mechanism that allows the system to transform raw data into useful information for monitoring and decision making. Here in this slide, you can see what is visible to end users through the TERRA platform interface. At the center, we can see the water pollution risk map, where each grid cell corresponds to a specific spatial area, and it is assigned a specific risk score. The numerical indicator help us quickly understand the severity of each zone, while the color scale make easier to interpret from say green areas and hazardous red zones. In addition, feature is the affected area here, as you can see, another feature, which highlights regions that may require attention or mitigation action by the authorities. Together, all these outputs allow users to visually understand where pollution is located, how severe it is, and which surrounding areas may be affected. In the next slide, we actually zoom in a little bit. We can see a more detailed view of the platform. And this is happening when a user selects a specific grid cell or a specific spatial area. While the previous screen focused on the overall pollution map, here we zoom in details about a specific zone and provide forecasting at historical trends. As you can see in the left side of the screen, the platform presents the water quality index together with estimated water flow direction, which help us explain and understand how pollution may continue to move. Below that, also users have the ability to explore historical trends over time. Thus, they can easily compare current conditions with previous weeks or previous months. This dashboard also provides detailed pollution metrics such as chlorophyll, cyanobacteria, DOM values, which help explain the underlying causes of the risk level. And at the same time, at the center of the map, here, for example, the selected grid is highlighted with its current numerical score, allowing the user to see the detailed analytics and the exact spatial location of the cell. Now, regarding the real-world value of our demonstrator for stakeholders, first, the system supports early warnings and intervention, allowing authorities using the pollution forecasting and risk indicators to have a proactive preparation. Second, it enables evidence-based decision by providing policymakers, water authorities, municipalities, researchers with an integrated view of how pollutions evolve, both in space and in time. And lastly, the demonstrator supports sectoral and coastal protection, especially for agriculture, fisheries, and economic activities located near the river or near the coastal area. All these benefits lead to the broader vision of Demonstrator 1, of our demonstrator, which is to provide a modern framework that connects science, technology, and policy support into one single unified operational platform. Finally, the demonstrator 1 shows how our AI models, hydrological understanding, Earth observation, and digital twin, all these technologies can work together to protect the important water ecosystems and to understand pollution, movement across the river deltas, that helps us actually to transform environmental protection from a reactive process into a proactive process. And that was from my side. Thank you. Paul?
Thank you very much, Panagiotis. I don't know if anyone has any question for Panagiotis at this point. Okay, if anything comes up later, please feel free to add your questions in the chat, and we'll address them at the end of the session. So let's move on to demonstrator 2, focusing on environments around seaports. I would like to invite Krzysztof Kanawka from Blue Dot Solutions. Chris, the floor is yours. Good morning. Good morning from all of us.
Thank you very much for this question. Let's start with the most traditional question. Is my presentation visible? See my presentation?
The presentation seems okay. Your voice is a little bit, let's say... Can you talk now?
Yeah, can you? Still?
We can hear you, but there are some, let's say, noises. Now we cannot hear anything. We will wait for you. No, we cannot hear you, Chris, unfortunately. Chris, we will move on to the next demonstrator and give you time to get in again. So let's move to demonstrator 3, focusing on coastal chains monitoring through a digital twin approach. I would like to invite Xiao from the University of Glasgow. Ke, are you here with us?
Yes, thank you for the introduction.
The floor is yours, and
Okay.
we will wait for Chris to get into the webinar again and
Sure.
give them the floor later. Okay, Ke, we hear you.
Hello, everyone, and thank you for joining. My name is Xiao from the University of Glasgow. In this presentation, I will introduce our work on a coastal digital twin for coastal change monitoring and prediction from satellite remote sensing. The idea is to move beyond single images and build a system that can observe, remember, and forecast coastal change. Here is the structure of the talk. I will begin with a short introduction to what we mean by a coastal digital twin, or we can call it coastal DT. Then I will explain how we define the coastal state and why this design is so important. After that, I will walk through the main methodological capabilities and the uncertainty-aware visualization, the full workflow, and finally where the system stands today and what our next priorities are. So this talk moves from concept to representation and implementation. This slide gives a high-level view of the coastal DT at the complete operational loop. We described through 5 capabilities. First, initialize. When a user selects a new area of interest, or we can call it AOI, the system needs to establish a usable geometric reference frame for that coastline. Second, perceive. That means turning the latest satellite scenes into a measurable coastal state. And third, remember, a digital twin is not just about the image, It needs a consistent memory of historical observation over time. Fourth, forecast. Based on the current state and the selected historical information, the system forecasts future movement together with the uncertainty. And fifth, visualize. The output needs to be converted into map-ready geometries that can be shown in the interface directly. So from the user's perspective, the interactions is very simple. The user chooses an AOI, and then the system handles the full life cycle from current observation to future forecast. We are not just building a detection model. We are building a stateful and end-to-end digital twin workflow. One of the most important design is what exactly should the digital twin track? At the first glance, the waterline may seem like the obvious answer because it's visually clear in the satellite image. But from a digital twin perspective, it's actually a bad choice. Because actually the word line is sensitive to tides and wave conditions. So it often behaves like a noisy, rapid boundary. It tells us something about the movement of image capture, but it's not always about the long-term environmental state. By contrast, the vegetation age, or we can call it VE, is much more stable across monthly and yearly timescales. It's more anchored in underlying coastal morphology, so it's much more suitable for temporal comparison. And that's why in our design, the vegetation age becomes the key state variable. In simple terms, if we want to build a real digital twin, we should not track a boundary that moves mainly because of the temporal tidal effects. We should track something that better reflects the underlying coastal condition, not short-term noise. So once we decided what to track, what the next question is, how do we make measurements comparable over time? Our answer is fixed geometry. There are three parts here. First, the anchor, or we can call it reference line. This defines where the measurement begins. Second, the transects, which acts like rulers placed across the reference line at fixed intervals. This defines where we measure. And third, we can say that is state variable, which is the distance from the vegetation age to the reference line along each transect. You can see these little white arrows here. If the measurement geometry changes every time a new satellite image arrives, then the time series becomes inconsistent. That means the measurements are no longer directly comparable over time. So by fixing the geometry once, we turn repeated satellite scenes into a persistent and comparable digital state. So instead of saying here is another image, we can say, oh, here is another coastal state measured in the same coordinate logic as before. This slide shows how we implement the first two capabilities. On the left, for a new AOI, we first need to bootstrap the geometry. For that, we use robust unite on a seed scene. Its role here is not to define a perfect ground truth. Instead, it works as a geometry bootstrapper. In other words, it helps us automatically generate the fixed reference line, like the yellow one, and the transect for a new coastal area. That is important because it reduces manual setup and makes the system more scalable when we move into a new location. Then, on the right, once the fixed geometry is in place, we use a VH-set-based method to extract the VE from the current scenes, like the green one. The VH set is a method developed by researchers at University of Glasgow, and here we bring that work into the coastal DT pipeline. Because the geometry has already been fixed. We don't need to start from scratch every time a new image comes in. We simply use the same reference frame to extract the current coastal state, the VE, in a consistent and repeatable way. So in practice, this becomes a hybrid strategy. A machine learning model helps us to set up the geometry for a new AOI, like the left side, and VH set-based extraction is then used to update the state within that fixed frame. This gives us a good balance between automation, repeatability, and interpretability. A digital twin also needs memory, but not all memory is equally useful. So in our system, we don't simply load the entire historical data every time. Instead, we use what we call strategic history memory. The idea is to combine two kinds of historical information. One is recent history because the latest observations are often the most informative for near future prediction. The other is same season anchors from previous years because coastal behavior often has seasonal structure. So for example, if we are here in the April 2026 and we want to make a prediction in April 2027, since from recent months are useful, but April scenes from earlier years may also be highly informative. This gives us a more selective and efficient memory design. So the system is not trying to remember everything, it's trying to remember the right things for predicting what comes next. This slide shows a key methodological shift in our forecasting design. One possible way to forecast coastline change is to predict a future 2D mask directly, like the blue area. But that approach is high-dimensional, it accumulates pixel-level errors, and is often difficult to compare or quality control over long time periods. By contrast, our approach is different. We reduce the problem into one-dimensional transect forecasting. Because the vegetation age has already been represented as distance along fixed transects, the forecasting target becomes a structured 1D temporal signal. That gives several advantages. First, it reduces the computing data dimension into 1D. Second, the output is physically meaningful. We are forecasting meters from the reference line, not just the abstract image pixels, have no meaning. And third, it becomes easier to compare results over time and across years. For the temporal model, we use a Mamba plus LSTM forecaster. Very briefly, the Mamba style components is useful for handling longer temporal dependencies, while the LSTM contributes stable sequential modeling. So together, they give us a critical balance between temporal capacity and robustness. That makes the system more efficient, more interpretable, and more compatible with digital twin logic. Another important part of the system is how we communicate uncertainty. In many technique systems, uncertainty stays hidden in the backend as log files. We want to do something more useful. In the coastline DT, uncertainty is visualized directly on the map as a geographic bound around the predicted mean line, with seaward and landward bounds. So the user doesn't just see one single predict line. They also see how uncertainty or the certainty that prediction is. That is important in environment monitoring because users need to understand not only the prediction itself, but also need some hints for what need to be cautioned. Okay. So uncertainty becomes something visible and actionable. This slide puts everything together into one end-to-end workflow. First, the user selects an AOI. Then the system establishes the fixed geometry. Next, it extracts the latest VE and evaluates the current state. After that, it loads the selected historical scenes. Then the forecasting model processes the 1D temporal input, and finally, the predicted distance are converted back into geographic output formats like GeoJSON, so they can be displayed and they can be used downstream. So basically, we have reorganized the coastline change problem into a workflow that is geometric stable, interpretable, and designed for online operation. To conclude, this is where the system stands today. What is already live is an end-to-end online main workflow. The system already operates as a trainable loop and is already support true coastal memory and forecasting logic rather than one-off extraction. Looking ahead, there are two major next priorities. The first is cross-AOI generalization. We want the system to be more robust when transferred to new areas. The second is moving towards more business and decision-facing metrics. So not only standard machine learning errors, but also more interpretable outputs. So the goal is very clear here. We are not trying to build another extraction tool. We are trying to deliver a usable coastal memory that can support monitoring, interpretation, and future prediction. Thank you very much for listening.
We thank you, Ke. Are there any questions for Ke and demonstrator 3? Okay, so let's now return to Krzysztof Kanawka.
Okay, let's see how it works right now. Is it better?
It's very, very good.
Okay.
We can hear you very well. So,
Okay.
Chris, the floor is yours.
Okay.
And
So first of all,
sorry for this transition. Thank you for your patience.
okay, no problem. Thank you very much. And I'm also very, very sorry. Something happened with my network, but I switched to another network and it seems that it works.
It
Nevertheless,
works very well.
my name is Chris or Krzysztof. I represent a partner in the TERRA consortium, which is named Blue Dot Solutions. Blue Dot is our planet Earth. That's why we are working for solutions for our planet Earth. And in this particular part of the TERRA project, we are responsible for preparation of two parts of one demonstrator. Both of them are related to seaports. One of them, that one that I would like to talk with you today, is about environment around seaports. This is part of our work. And the second part, which I hope that we will be able to cover at a later webinar, is related to detection of illegal and potentially illegal activities of ships around seaports. This is a little bit more complex part, and we will cover it later as the work is simply ongoing. Nevertheless, the motivation for our work is related to the fact that a big part of our economy is simply related to seaports. Basically, a huge part of goods, a huge part of logistics, huge part of energy, huge part of shipping activities are simply related to seaports. And this is a very, very global issue and a very global trend. Many seaports, including smaller and medium-sized ones, they are increasing their traffic, and it's counted in millions of tons, which is a very, very big value. So you really have to put a lot of control and then a lot of environmental monitoring around seaports. This is very, very important because, well, the more activities related, the more human activities related to seaports will, of course, impact the environment. And if the environment is impacted, of course, the results might be quite severe. So there might be a problem, and this is a huge issue, especially if you consider also the fact that not every country is directly connected to a seaport. Not every country has access to the sea. So in some cases, in some parts of the world, and also in case of Europe, some seaports, they are, you can consider them as a gateway to the rest of the part of the continent, to other countries, which of course increases the pressure to increase the economic operations at such a place, and of course it can be at the expense of the environment. Finally, one thing that is very, very important part to note here is that although it is clear that seaports are mandated to provide a lot of information about the environment, both on the air, both on the land, and both on the seaside, uh, there's no clear indication that such information always would be provided in a transparent way. In fact, there's quite a number of countries that do not wish to cooperate with other countries, and of course they provide very little information, especially about the environmental activities. We see this also across Europe. That's why we feel that adding into the TERRA project all the information about monitoring the environment would provide a lot of very valuable information, especially if you consider satellite data, if you consider advanced mathematic models that could be used by the TERRA platform, and then it would be displayed in such a way that the data would be very well visualized and it would provide a lot of useful information. So this is what we would like to do in this particular case of the TERRA project in this part of the demonstrator. We are focusing on two different parts when it comes to environmental control, on the land side and then on the water side. On the land side, it is clear that seaport infrastructure, especially if it grows, if it's bigger, it can impact the surrounding land. So you talk about deposits of raw materials. We can talk about pollution. You talk about effects on local vegetation. All of such information can be considered and can be checked to be seen and to be verified in such a way by the environment. So this is a very, very important part, and this is very, very important. This is very, very important activity that would require constant monitoring. In this particular case, you can use typically used indexes such as the famous NDVDI, for example, that you can use, but you can also provide some additional information. And in total, such a demonstrator, we feel that would provide very valuable information on the land side, and the same side would be on the water side. Here, the situation is a little bit different because, first of all, the water side, the water environment is very dynamic. So, of course, you can provide a number of information, but you have to be very careful when it comes to proper analysis and interpretation of the data, because there will be always some activities around the seaport, and there will be some infrastructure, for example, around the seaport that could potentially change or impact the way the water, for example, moves. But at the same time, there can be, for example, mouth of a river, for example, and might be several different rivers. There might be some more complex interactions between the seawater, the land, the water, and of course the fresh water, for example, that comes from rivers. So it's important to watch it, to monitor it and check it. And in our case, we decided to provide information, for example, about the dissolved organic matter and chlorophyll concentrations, so that you would be able to provide you would be able to check and verify the information related to changes in time, maybe also changes in the concentration around some limited areas or some constrained areas, for example, by the infrastructure, where there might be significant differences between the open sea, for example, rivers, and such areas, for example, in chlorophyll concentrations. This is very important because all together, all of those information would be fed to the TERRA platform, which would provide and visualize information, and that there would be several different parameters, all presented in one place, where you could see also of a large temporal area, a large temporal space, so in a longer time series, you could see the differences and changes that could have happened, not only in a short term or very, very short term, but also over longer historical periods, for example, 5, 7, 10 years. This is what's possible with the help of the Copernicus data, because the data is already available for at least 6, 7, 8 years, which already allows us to verify longer term activities. So basically speaking, this is our part of our work on the demonstrator. We are right now working on those two parts of the demonstrator. Both of them related to done on an example of a seaport of Gdańsk. This seaport is located on the shores of the Baltic Sea, on the southern shores of the Baltic Sea, next to a river, next to a river mouth, and also in a very complex hydrological conditions when it comes to the currents, changes of direction of currents, and of course interaction with the land. I just covered in this short presentation the part of the environmental monitoring, and the second part of our demonstrator is focused on potentially illegal activities and potential strange behavior of ships, and we would combine IIS-based vessel traffic with SAR data. So that's all from my side. Thank you very much for your attention, and if there are any questions, I'm ready to answer them. Thank you very much.
Thank you, Chris. I don't know if any one of you has direct questions to Chris. Okay, that was a really strong set of presentations. Thanks to all speakers. Very clear and very engaging slides. Thank you. So let's move on to a Q&A session if needed at this point. If you have any questions, please feel free to write them in the chat or raise your hand. Any question? Any hand to be raised? Okay, so let's wrap up the session. Thank you all for joining us today and for your participation, the speakers. We look forward to sharing more updates and results from TERRA in the coming months. So thank you, and have a nice day to all of you. Thank you.
Thank you. Bye.
Thank you, Sophia. Bye.
Thank you very much.
Thank you. Bye.
Thanks. Bye-bye.